Hi, my name is Ahalya Prabhakar, and I'm part of the LASA lab at EPFL. And today I'm going to talk about our work on multimodal sensory learning for real-time adaptive manipulation. So our goal in this work is to enable robots to safely hand over objects with unknown contents and properties to a human without dropping the object during manipulation and without injuring the human during handover. To do so, we want to enable the robot to both predict in real time the contents of the container and its corresponding inertial properties, as well as use the predicted information in an adaptive controller to maintain a stable grip on the container during manipulation. To do so, we approach this problem using multimodal sensory fusion, specifically tactile data and audio data, to quickly estimate the material contents and their corresponding inertial properties. Specifically, we use audio data for material classification. We use a microphone that is attached to the robotic hand holding the container to record and classify the sounds of the contents inside the container during motion to identify which material it is. We also use tactile data coming from TechScan sensors mounted all over the Allegro hand, collecting pressure data, as well as the Allegro hand joint data itself, and use that to predict the torque that will be experienced by the robotic hand and compensate for it during control. To actually acquire data for training these networks, we collect data with two different types of motions on a KUKA IVA robot with the Allegro hand mounted on it, holding the container. We train it with two different types of motion, specifically rotation motion, where we rotate the container a specific number of times, as well as with vertical shaking to shake the container such that the contents inside move and produce noise. We collect a full data set with this setup for both types of motions, vertical shaking and rotation, and for 5 different material classes, one where the container is empty, as well as 4 different materials with different properties, specifically rice, cornflakes, gummies, and vitamins. We collect 30 trials for each class for a total of 300 trials. We did some preliminary analysis on this data set we collected. Using the audio data, we used a CNN classifier using MFCC coefficients, and we were able to get accurate classification of motions and materials entirely from the audio signals. However, this is using the audio signal for the full motion to classify. We plan to extend this by reducing the time needed for classification in order to enable real-time classification. We are also looking at the tactile signal coming from the TechScan sensors. On the left, we show the mask of the TechScan sensors on the Allegro hand with all the pixels activated. On the right, we see the activation of the TechScan sensors over a motion, specifically the rotation motion of the cornflakes. We see that as the objects rotate inside the container, the pressures moving along the hand itself are visible. The goal is to use this to anticipate when the high torques will be experienced by the hand and compensate for it during control. So overall, our goal here is to quickly estimate the container properties with safe motion, which we can then use in an adaptive controller during robot manipulation for object handover. We are currently working on training the networks to quickly predict both the contents and their inertial properties in real time to classify the material contents and predict the torque that will be experienced. In addition, we plan to develop an adaptive controller that uses the learned information to anticipate for and compensate for the torque that will be experienced. In addition, the data set we have collected that contains the motion trajectories of the IVA robot, as well as the Allegro hand joint data, the TechScan sensor pressure data, and the audio data are all publicly available on our lab website. Thank you so much.